Hi students, welcome to Sunil's tutorial. I'm Sunil Kirwani and today we will be doing this chapter called as magnetism. Now let's try to look at a magnet, guys. This is your bar magnet. Let's assume that the length of the magnet, the geometric length, this is my geometric length. We call this as GL. This is my geometric length. But this is your length from one end of the bar magnet to another end of the bar magnet, but the poles are not situated at that place. They are not situated at the end. North pole is situated somewhere here, south pole is situated somewhere here. So what you will see is that the magnetic length is always less than the geometric length. The magnetic length of a magnet is always less than the geometric length of the magnet. Now the relationship between them is that magnetic length of a magnet is equal to 5/6 times the geometric length. The relationship between magnetic length and geometric length is that magnetic length is 5/6 times the geometric length. Fine, do we get this in clear? Now, what do we understand by magnetic dipole moment? What do we understand by magnetic dipole moment? Right? Magnetic dipole moment is defined as the product of pole strength and the magnetic length. Magnetic dipole moment is defined as the product of pole strength and magnetic length. That is, magnetic dipole moment is pole strength into magnetic length. Henceforth, we will be writing magnetic length as 2L. Right? Now, once you have done this, now let's see this. Let's try to find out what is torque. Very important concept. A lot of students once you go in 12th, even then you don't understand what is torque. Now see, if I have a body, if I apply force on a body, the body will move in a straight line. If I apply force on a body, if the body moves in circular motion, then that force is called as torque. What is torque? Torque is a force that produces circular motion. Torque is a force that produces circular motion. Right? Now let us try to find out torque in a torque on a magnet in a uniform magnetic induction. Now let's see this. Let's assume that you have a bar magnet which is obliquely placed in a magnetic field. Right? Let's assume that you have a bar magnet which is obliquely placed. So let's assume that you have external magnetic field. This is your external magnetic field. Right? Let's assume that this is your magnetic length, right? Where this is your south pole and this is the north pole, right? Now, when it is placed in an external magnetic field, there's an external magnet placed here. I'm keeping a magnet in an external magnetic field. There will be two forces acting on the magnet. One, the north pole is going to be pulled in the direction of the magnetic field, right? And the south pole is going to be pulled in the direction opposite to the direction of the magnetic field, right? Now let us try to find out what is the perpendicular distance between the two forces. How do I find that out? Drop a perpendicular here and join this, right? In which case you will get this point as, say, P. Okay. Now, with what force will this North pole move in this direction, it will move with a force equal to the pole strength multiplied by the external magnetic field. This will move in south direction, same, minus mb with a force of minus mb. Fine. Let us assume that the magnet makes an angle of alpha with the external magnetic field, right? So let's write this much down first. Consider a uniform magnetic field of induction, uniform magnetic field of induction B. Let us assume that alpha is the angle made by the axis with the direction of the magnetic field. Is the angle made by the axis with the direction of the magnetic field. Right? Now, let's assume that the length of the magnetic length is 2L. Magnetic length is say 2L, and let's assume that the pole strength is equal to M. In which case, I can say that magnetic dipole moment M is equal to M into 2L. Magnetic dipole moment, this will be your magnetic dipole moment. Now, as the magnet is placed in a uniform magnetic field, the north pole is going to be acted by a force of MB, and the south pole is going to be acted in the opposite direction with a force of minus MB. These two forces are equal in magnitude, opposite in direction, and acting at different points. Right? I can say that since magnet placed in external magnetic field, the north pole is acted upon by a force of MB, and south pole by a force of minus MB. Right? Now these two forces are equal in magnitude, opposite in direction, and act at different points. This is what gives rise to a couple, right? So in that case, which gives rise to a couple, torque is also called as couple, which gives rise to couple. So what do you mean by couple? Couple means two forces which are equal in magnitude, opposite in direction, and act at different points. Right? These are two forces which are equal in magnitude, opposite in direction, and act at different points. How do I write the formula for this? Couple or torque is the same thing. Torque is given by the formula any one of the force multiplied by the perpendicular distance between the two forces. Right? So in that case, in our diagram, torque is going to be any one force, that is MB, multiplied by the perpendicular distance between the two forces. From the diagram we see that the perpendicular distance between the two forces is NP. Right? Now, let's consider in triangle NSP. In triangle NSP, I can say that if this angle is alpha, I can say that sine alpha is nothing but opposite upon hypo. Sine alpha is going to be opposite, which is NP, upon hypo, which is going to be NS, right? So in which case I can therefore say that NP is equal to NS sine alpha. So NP is equal to 2L sine alpha, right? Substitute here. So in which case I will get torque is equal to MB into NP. NP is nothing but 2L sine alpha. Now this can be written as B into M into 2L sine alpha, right? But M into 2L, pole strength into magnetic length, is nothing but magnetic dipole moment. M into 2L is capital M sine alpha. Now from scalars and vectors we have learned that the multiplication of two vectors, two numbers, with the sign of the angle between them is nothing but cross product. So T vector is going to be equal to nothing but MB sine alpha, which can be written as M vector cross B vector. Fine, do we get this thing clear? So do we understand torque? So how do I define torque? The magnetic dipole moment, this is going to be your torque. It is a force that is going to produce circular motion. It is defined as a product of the magnetic dipole moment, external magnetic induction, and the sign of the angle between them. Fine, do we get this thing here? Now, if magnetic induction, the external magnetic induction is 1 and alpha is equal to 90 degree, then sine alpha will also be equal to 1 because sine 90 is 1, in which case torque, which is equal to MB sine alpha, will be M, B is 1, sine alpha is 1, then torque will become equal to magnetic dipole moment, right? So thus I can say that the magnetic dipole moment of a magnet can be defined as the torque required to hold a magnet with its axis perpendicular to the uniform magnetic field of unit induction. I can also define magnetic, therefore I can say that what is magnetic dipole moment? Magnetic dipole moment can be defined as the torque, here see M is equal to T, so torque required to hold a magnet with its axis perpendicular. Remember, alpha was 90 degree, with its axis perpendicular to uniform magnetic field of unit induction. Right? That's how you define magnetic dipole moment based on torque. Right? Next, let's see another law now. Let's see the tangent law. Now, instead of placing the magnet in one magnetic field, if I place the magnet in two external magnetic fields, for example, let us consider that this is my magnet, right? There are two external magnetic fields. This is one magnetic field in this direction B, and let us consider that there is another magnetic field in the direction BH. Right? Let us assume that this magnetic field is in the horizontal direction and its force is say B, and the other is, instead of BH, let's call this as B bar. The other is in vertical direction and let us call this as B bar. This is the north pole, this is the south pole of the magnet. The distance between them is 2L. Right? Now, the north pole, what are the forces that are going to act on north pole? One, force here, which is going to be MB. Force here, which is going to be MB bar. Similarly, on the south pole, two forces. Force here, which is MB. Force in upward direction, which is going to be MB bar. Right? Let's try to find out the perpendicular distance between the two forces. Let's drop a perpendicular from the south pole. Let's call this point as, say, P. Let us assume that the axis makes an angle of theta with the horizontal magnetic field. Right? So let's write all these assumptions down. Consider a bar magnet. Consider a bar magnet suspended in two uniform magnetic field of inductions B and B bar, right, which are mutually perpendicular to each other, perpendicular to each other. So B and B bar are perpendicular to each other, right? Now, let's also consider that let the axis of the magnet make an angle of theta with direction B vector, right? Now, let's assume that M is the pole strength, 2L is the magnetic length, right? And M is the magnetic dipole moment. In which case I can therefore say that magnetic dipole moment is M into 2L. Let's leave that there. Now, I can say that there are going to be two torques that are going to be acting here. First, let us consider the torque due to B. Torque due to magnetic field B. Now, torque is nothing but force in the direction multiplied by the perpendicular distance. Now, the distance, guys, if you look at the diagram, the distance between the two MBs is going to be nothing but SP. The perpendicular distance between them is going to be nothing but SP, right? So let's call this torque as, say, T. Now, in that case, in triangle NPS, I can say that sine theta is nothing but opposite upon hypo, and cos theta is nothing but adjacent upon hypo. Therefore, I can say that SP is equal to 2L. NS is nothing but 2L. 2L sine theta and NP is 2L cos theta. So here I will get torque is equal to MB into 2L sine theta. Right? Leave this here as it is. Maximum I could do is, I could say B into M into 2L sine theta. So torque is equal to B into magnetic dipole moment into sine theta. Similarly, I can say torque due to B bar. Torque due to B bar. So let's call this as T bar, is going to be nothing but MB into the perpendicular distance between them. The perpendicular distance between them, guys, is going to be nothing but NP from the diagram. The perpendicular distance between MB bar, the perpendicular distance between MB bar and MB bar is going to be this, which is going to be nothing but NP, right? So in that case, I can say T bar is MB bar into NP. NP is nothing but 2L cos theta. This can be written as T bar is equal to B bar into M into 2L cos theta. Therefore, T bar is equal to B bar into M into cos theta. Right? Now, since the magnet is at rest, the two forces that are acting on the magnet should be equal, right? That means I can say that T should be equal to T bar. It is only when T is equal to T bar will the magnet be at rest. Now T can be written as Bm sin theta, right? T bar can be written as B bar M cos theta, right? M and M gets cancelled, so I'll get B bar is equal to B sin theta upon cos theta. Therefore, I can say B bar is equal to B tan theta, right? That means I can therefore say this is what is my tangent law. B bar is equal to B tan theta. So how do I write this? How do I define tangent law? This was the derivation of tangent law. How do I define tangent law? If a bar magnet is suspended in two mutually perpendicular uniform magnetic field, B and B bar, and it comes to rest with its axis at making an angle of theta. With the direction of B, then B bar will be equal to B tan theta. That's how you define tangent. Right? Do we understand that? We'll stop this here for the day. Thank you very much.